Every time you eat, you open a high-traffic international port. The gastrointestinal tract is an active biological checkpoint, evaluating millions of foreign particles daily. The primary security perimeter for this checkpoint is the intestinal epithelial barrier. It is exactly 1 cell thick, standing between your internal blood supply and a constant influx of environmental threats. A healthy gut is defined by its resilience. It processes high volumes of diverse inputs, like a sudden influx of varied street foods, without the structural system suffering a collapse. When the physical integrity of that single-cell layer fails, foreign material breaches the perimeter. That structural failure is the baseline for chronic inflammation and systemic metabolic dysfunction. To keep the checkpoint running, the system relies on microbiota-accessible carbohydrates, or MACs. These are complex plant fibers that human digestion is incapable of processing on its own. Instead, the body employs specialized microbial worker guilds. Strains like Bifidobacterium set up shop along the barrier to ferment these raw botanical materials. In this fermentation process, a complex fiber molecule locks into a bacterial node, converting into glowing particles called short-chain fatty acids, specifically butyrate. This metabolic currency provides up to 70% of the energy required by the cells lining the harbor. The gut economy relies on functional redundancy. If one microbial guild is hindered, a different species can step in and continue manufacturing that energy currency. An energized cellular wall maintains an inhospitable environment for invaders. That structural strength prevents normally harmless microbes from sensing weakness and acting as pathobionts. That structural strength is tested when the system is flooded with biologically unstable goods. Under the NOVA framework, these industrial formulations are classified as ultra-processed foods, or UPFs. We can see the mechanical damage in this cellular cross-section. Industrial emulsifiers act to dissolve the gut's protective moisture layer, leaving the underlying cell wall totally exposed. Without that barrier, bacteria make direct contact with the wall. The immune system loses its immunological tolerance, the ability to ignore friendly cargo, and enters a state of chronic alarm. A high influx of ultra-processed cargo leads to active physical erosion of the body's primary immunological infrastructure. High-temperature cooking introduces a different threat: thermally damaged lipids. Frying foods creates oxidation byproducts that seep directly into the digestive checkpoint. These oxidized oils trigger localized inflammatory fires and shift the microbial demographics toward aggressive, toxic-resistant strains. This visualization tracks the resulting shift. As the Fried Food Microbiota Index, or FMI, rises, the android-gynoid ratio chart shifts alongside it, showing that metabolic debris is being stored specifically as abdominal fat. In response to the toxic buildup, elite security cells called macrophages attempt to absorb and clear out the oxidized cholesterol waste. The defense fails when the macrophages consume so much fat they become bloated and immobile. These foam cells cause a total cellular gridlock within the harbor. The scale of disruption changes significantly when the system is introduced to a harsh foreign chemical compound, such as a heavy course of antibiotics. This xenobiotic storm causes a taxonomic collapse, indiscriminately destroying both the loyalist workforce and harmless stowaways. As the microbial community decays, it releases endotoxins that flood the system and trigger global metabolic distress signals. Frequent storms allow unauthorized microbes to build biological armor. This results in antimicrobial resistance, a condition where pathogens become nearly impossible to evict. Over time, the harbor can enter a state of stable dysbiosis, a long-lasting imbalance in the microbial community that is resistant to returning to health. Recovering from these disturbances requires a rebuilding phase, led by recovery-associated bacteria, or RABs. These master builders possess high adhesion capabilities, allowing them to stick to the harbor walls and resist being washed away while they coordinate the reconstruction of the moisture layer. Paneth cells act as border guards by manufacturing antimicrobial peptides, or AMPs. These peptides attach to and dismantle invading pathogens, leaving barrier tiles intact. With the perimeter secured, RABs use cross-feeding to share nutrients with worker cells, jump-starting the production of short-chain fatty acids. Establishing colonization resistance requires this combination of targeted chemical defense against invaders and aggressive resource sharing among the loyalists. As the walls are repaired, the secondary problem of gridlock remains. specifically the bloated, immobile macrophage foam cells blocking the harbor's security channels. Clearing this requires specific chemical signals. Phytochemicals like naringin, found in citrus, can be introduced to signal the security forces to export excess fat. Naringin upregulates cholesterol efflux transporters. These proteins act as biological pumps to move toxic fat out of the cells and back into systemic disposal channels. Cooling down the inflammatory fire requires these natural regulators to restore the harbor's security detail to peak performance. Future trade is best regulated through symbiotics, a combination of elite probiotic recruits and the specific prebiotic fuel they need to thrive. Feeding beneficial recruits like Akkermansia muciniphila ensures they naturally outcompete unauthorized stowaways for space, a principle known as competitive exclusion. By proactively dictating this biological supply chain, the system maintains the metabolic flexibility needed to handle modern dietary storms while keeping the internal harbor operational.